Hello students, this is Dr. Ben. I'd like to work on another problem out of Chapter 8 that has to do with the concept of rotational equilibrium. So here we see in this picture that we have a house painter on a scaffolding that's held up by two ropes. We're given some information about the painter in the geometry of the scaffolding itself, and we're asked to find out the value of the forces in each of the ropes that are holding the scaffolding up. So in the first part of the problem, we want to find the force on the left-hand rope, and we're going to do that by using net torque equals 0. And then in part B of the problem, we'll find the force on the right-hand side in a similar manner. Alright, so let's draw a force diagram for the painter. So we can already see the two forces in the ropes on the diagram. So let's add a weight of the painter and a weight of the platform itself that's located at its center of mass. And for part A of the problem, I would like to pick my pivot to be at the right-hand end, because then that will allow me to find the tension in the left-hand rope. Alright, so we see that there are four forces that act on the platform, but only 3 cause torque. In this case, the force due to the right-hand rope does not cause any torque because its moment arm is equal to 0. So the net torque equals 0 will be the sum of 3 different terms in our problem. There will be the torque due to the left-hand rope, plus the torque due to the painter, plus the torque due to the platform itself has to be equal to 0. And then each of those terms is going to have the form r times f times the cosine times the sine of an angle. Alright, so the torque due to the rope that's on the left will be equal to F sub L multiplied by the length L, which is the distance from the pivot point to the point of application of that force, times the sine of 90 degrees. And we have to put a minus sign in front of that because that torque causes a clockwise rotation. The torque due to the painter will also be counterclockwise, so it will be positive, and that will be capital mg times the distance L minus d. So the painter is 3 meters away from the right-hand end, times the sine of 90 degrees. And then the torque due to the platform itself is going to be positive mg L over 2 times the sine of 90 degrees. So the only number that we don't know in this expression is the force due to the left-hand rope, so we can go ahead and solve for that. So I'll have mg L minus d times the sine of 90, which is 1, plus little m g L over 2 times the sine of 90, which is 1, is equal to F sub L times 1. So I divide through by L, so I get that F sub L is equal to mg L minus d over L plus little mg over 2. So for our particular numbers, we need to go back, find the painter was 75 kilograms and the platform was 20. So we will have 75 times 9.8 times 5 minus 3 over 2, so that's going to be 2/5, 5 minus 3 over 5, plus 20 kilograms times 9.8 divided by 2. Alright, so we get our calculator out. So we'll take 75 times 9.8 plus 20 times 9.8 divided by 2. So that equals 833 newtons. So the force due to the rope on the left-hand side of the platform is equal to 833 newtons. Alright, so to do part B of the problem, in order to find the right-hand tension, the rope in the tension in the right-hand rope, we can either use the same procedure and set the net torque equal to 0, picking any other point as our pivot, or we could just go ahead and use Newton's first law, because we realize that in the y direction the net force acting on this platform has to be equal to 0. So that's probably the simplest way to go. F net y equals 0. So that would tell us the force of the left-hand rope minus the weight of the painter minus the weight of the platform plus the force in the right-hand rope has to be equal to 0. And if we would solve that, then the force in the right-hand rope would be equal to big mg plus little mg minus F sub L. So this will be 75 times 9.8 plus 20 times 9.8 minus our 833 that we found in part A of the problem. So I'll just take 75 plus 20 times 9.8 and then add to it 833, and so that gives us 1764 newtons, and that will be the force in the right-hand cable. I probably should round that to 1760 newtons. Alright, so there we go. We found the force in the left-hand cable by using a rotational equilibrium condition, and then we use Newton's first law in order to find the tension in the right-hand cable.